Hi, so today I'm going to talk about differentiation and derivatives of functions. So firstly, let me introduce the concept of differentiation. The concept of differentiation simply means to take the derivative of a certain function f(x). I apologize for my messy handwriting. It's very difficult to write on a computer, which isn't very surprising at all. So we use the d over dx symbol to denote a derivative of fx. So this thing, the x in the denominator indicates what variable you are differentiating. It could be d theta, d y, d alpha, ... It could be any variable as long as the function is based on that variable. So the definition of the derivative is that the derivative of function fx measures the rate of change in that function. So that's a very simple definition. It's also quite useful in physics because it can measure the velocity and acceleration of an object. But that's besides the point, and I'm digressing. Let me tell you about how to evaluate the derivatives. So firstly, let's take a derivative of a constant c. The derivative of a constant c equals 0, because a constant never changes. There's no variable in a constant. So this is this is fairly easy to comprehend. Let's move on to something more complicated, like a variable. So if you were to differentiate this function f(x) equals x, the derivative of x simply equals 1. Why? Because when you plug in integer values of x that are successors of each other, i.e. 1, 2, 3, ... you plug in these values for x. As you can notice, x changes by 1 each time. Therefore, the derivative of x is 1. Now, what if we had something with a coefficient, some variable with a coefficient, like 3x? All you have to do is to put the 3 in front of the derivative operation, so that it becomes 3 times d dxx, so that this is 3 times 1, which equals 3. Very simple. Now, one of the most important rules in differentiation is the power rule, which states that x to the n equals the derivative of x to the n is equal to n times x to the n minus 1. This is useful in integrating more complex functions. Now, another rule of differentiation is that states that when you're trying to differentiate a function that's made up of several parts, such as 3x plus x squared, it simply equals the derivative of all these parts added together. So this function now equals the derivative of 3x plus the derivative of x squared, which equals 3 plus 2x. And yes, this is very simple. So now that we've learned about the basics of differentiation, let's start with some practice problems. So I thought we'd start with something very simple, such as the derivative of 3x. This now equals the 3 times the derivative of x, which equals 1. 3. Sorry. So that was a very easy example. Now move on to some more complex questions. Let's take the derivative of x to the third. This equals 3x squared. Why? According to the power rule, something with a x to the nth power the derivative of x to the nth power is equal to n times x to the n minus 1th power. So we can simply pull this exponent to the left side to be the coefficient of x, and then subtract the exponent by 1 to get the new exponent. Very simple. So now that we've gotten over those two very simple examples, let's get to something more difficult: trigonometric functions. For example, sine x or cosine x. What are the derivatives of that? So as you can basically infer from the name, sine and cosine, those two functions are derivatives of each other. Well, technically, one of them is a negative derivative of another, but I'm digressing again. So the derivative of sine x is equal to cosine x. The derivative of cosine x is equal to sine x. So, sorry, I made a mistake there. The derivative of cosine x is equal to negative sine x, not sine x. So, this is all quite simple, actually. It's very easy to comprehend. So let's move on to our next example. We have a function that's comprised of three parts: 3x plus x squared plus 2x to the third. Now, we can split this up into the sum of derivatives of each part. So we take the derivative of 3x, we take the derivative of x squared, and then we take the derivative of 2x third, and we add them up together. So this equals 3 plus 2x plus 3 times the derivative of x squared, x cubed, which equals 3 plus 2x plus 3 times 3x squared, which equals 3 plus 2x plus 9x squared, which is our final answer. So what about another example of trigonometric functions? So let's differentiate cosine x plus sine x. This equals, so first what we do is split this up into the sum of the derivative of each part. So this equals cosine x plus the derivative of cosine x plus the derivative of sine x, which equals negative sine x, as stated before, plus cosine x. This turns out very nicely. So, what happens after the first derivative? Obviously, we can differentiate again. So this is something called the second order derivative, where you differentiate the first order derivative of a function. Let's say we have a function x squared. The second order derivative is defined as the derivative of x squared, then taking the derivative of that, as shown below. This is denoted d squared dx squared. And in general, the nth order derivative is equal to d to the n over dx to the n. So let's try to take the second order derivative of a function. Let's say x squared. This equals the derivative of x squared. This equals the derivative of 2x. I know I don't really have to put the parentheses there, but okay. So the derivative of this is 2. Because when you have a simple variable at the first degree, you simply remove the variable and leave the coefficient behind. So this is very simple. What about third order derivatives? For example, for x for x to the third. This equals the d dx iterated 3 times of x third, which equals d dx 3x squared, which equals d dx 6x, because when you take the derivative of x squared, it equals 2x times 3, this equals 6x. This equals 6. So I wouldn't really mention this, but as I stated before, in physics, okay, I'm getting off topic here, but I'll just mention this. I won't go in depth in this. If you had the function of an object's motion fx, the first order derivative of x fx is the acceleration, the velocity of the object, or the rate at which fx changes. The second order derivative of x fx is the acceleration, the rate at which velocity changes. The third order derivative of fx is jerk. Yes, jerk. I'm not kidding. I have no idea why they named it that. The rate at which acceleration changes. The fourth order derivative is named snap. The fifth order derivative is named crackle, and the sixth order derivative is named pop. Yes, like the cereal brand. I have no idea why they named it that, but I'm digressing. Thank you everybody for watching this, the first video on differentiation. I have just covered the basics in this video. I will be going on to some more complicated topics of differentiation in the next video. Thank you.